could you do a quick intro?
We are.
That's fine.
All right, good afternoon. So we've seen the seminars this week. So the first one today, finding Boyle and SKA.
Thank you very much, Tom, and thank you all for coming up. Sorry to add to your heavy seminar list this week. 27 years ago, I came to Durham as a young, impressionable PhD student, and I was really very fortunate indeed to have a tremendous supervisor who took me on board and really enthused me about the opportunities in wide-field astronomy. And yes, he's here today in the audience. I thought I'd get in first, Tom, before you got me back. So I dedicate this lecture to Tom for being the inspiration behind me. Okay, well, I'd like to give you a quick update on a project, quite an exciting project called the Australian SKA, or Square Kilometre Array Pathfinder. It's a project that's well underway now. The idea of the Australian SKA Pathfinder is to build a wide-field radio survey telescope, basically a radio Schmidt telescope. This is part of Australia's participation in the International Square Kilometre Array Programme, and that this telescope is going to be developing technologies that we hope will be used in the Square Kilometre Array, most particularly the technology of the phased array feed. That is the ability to wide field radio telescopes, a radio camera, if you were, at the focal plane of the telescope. So rather than use a single feed, or indeed multiple feeds, is to bring all those together into a single contiguous array of pixels, if you like, albeit only a 10 by 10 array, but nevertheless a significant advance on what's been done before. Another goal of this project is to develop a new site for radio astronomy, which we call the Murchison Radio Astronomy Observatory, what we think is one of the best sites for radio astronomy on the planet because of its isolation. And another goal of this project was to build a strong research and development relationship with industry that will be essential if we are not only to build the SKA, but also to convince governments to put significant amount of money into these sorts of infrastructures in terms of the long-term industrial benefits of all of this. People always ask me at the outset, or after, if I haven't mentioned it, how much does all this cost? The actual total cost for the Australian SKA Pathfinder is $110 million. You can add to that $80 million for the high-performance computer required to process the data, and another $35 million and above for various forms of the infrastructure, including the fibre optic to get the data from the telescope site to the high-performance computer, which will be located in Perth, and also, of course, issues to do with power and powering this telescope, renewable energy options, and I'll discuss all that. So in total, we're looking at an investment the Australian government has made in this project over the last 2 years of over $200 million. That's all new money outside of the normal astronomy regime. So it demonstrates that you can actually get support for projects like this outside the normal astronomy vote. Okay, let's turn this around, it's a bit more convenient. So, what are the specifications of the Australian SKA? I presume people can interrupt. You can butt in like mindless animals if there's anything that you don't understand. So please go ahead. Specifications will be 36 12-metre antennas with a phased array feed located in the Midwest region of Western Australia. System temperature goal is 50 Kelvin. Well, we were confident about getting 50 Kelvin. We'd like to take it down to 35 Kelvin. With a frequency range between 700 megahertz and 1.8 gigahertz, and an instantaneous bandwidth of 300 megahertz. Resolution will be down to 5 kilohertz, and a field of view, as I said, of 30 square degrees. These sensitivity numbers are a little bit opaque for the non-cognoscenti in radio astronomy, for some of the cognoscenti in radio astronomy. But I thought I'd try to illustrate the rapidity of the speed of the potential survey that could be done with ASCAP by just showing you this particular image. This is a beloved radio galaxy, SEN-A. This is a composite image made from the VLT, Chandra, and VLA data. This is a typical field of view of a radio telescope, small dish radio telescope, typically 22 meter dish for the compact array. If we shrink it down to this size, that would be the field of view of the ASCAP, and indeed that's an image that was taken, just released a couple of weeks ago, of SENA by mosaicing together 400 compact array images taken over 1,200 hours of observing time, or 2 years of actual time. It's actually a rather beautiful image. I show it no more than just gives you an idea of the actual extent of the radio emission from SENA beyond the original little image that we're all familiar with. So that basically these things extend of the order of 300 kiloparsecs in either directions from SENA, almost about 10% of the distance back to our own Milky Way galaxy from SENA. So it does show you the power of being able to do wide field imaging. Unfortunately, with wide field imaging, with most telescopes that can reach these sorts of depths, you have to do these massive mosaicing and huge campaigns. It took us 1,200 hours to do this with the compact array. ASCAP would do this in 5 minutes. So it gives you a sense of the panoramic quality of this. And I should also point out, this is done by Ilana Fain, who's the ASCAP project scientist, along with Simon Johnson as well. So a lot of the stuff that you'll see when I talk about the survey science programs has been facilitated by Ilana, who's doing an absolutely wonderful job there. But it's a fantastic image. In fact, you could start talking about all this image all day, but you can see the different structures in the various radio lobes outside it. Okay, well, when is it going to be? Well, we're just about to put the first antenna on the site in next month, in December of this year. And we'll install the optic fibre that goes from the site back to initially to Geraldton. It's about 300 kilometres of optic fibre the first quarter of next year. We'll have a 6 antenna system ready by February of 2011. Install the full digital system. The 6 antenna system will have a preliminary back-end digital system installed. The full digital system will be installed in September 2011. The high-performance computer to process the data in 2012, of course, towards the end of this period. You don't want to put in the high-performance computer too early because, of course, it becomes obsolete, courtesy of Moore's law, within a few months. And then ASCAP science will start rolling out from December 2012. The array configuration, here are the 36 antennas. This might be a bit too faint for you to see, but you can see they're distributed over a full range and distance of 6 kilometres. It gives rise to a resolution of the order of 15 arc seconds on those baselines at 1.4 gigahertz.
Is there a reason to not have it symmetric?
To avoid as many redundant baselines as possible. No, it's not caused by the terrain. No, it's not caused by the terrain. Believe you me, because the terrain is actually largely flat, but there are floodplains and there are sensitive areas of native title, of indigenous sensitive areas that we have to avoid. Not very large, but essentially we're largely unconstrained by those. This was actually decided by the toss of a coin, literally, because the survey teams, because they were trying to optimize the array for a whole number of things in terms of how centrally condensed it was for things like pulsar timing surveys, or how widely spaced it was for continuing imaging surveys to avoid confusion. They were arguing, so I eventually tossed a coin and said, right, the one wins. And of course, it landed the wrong way up, and they go, oh, don't like that. I said, well, there you go, that's the answer for you. So we chose the other one. So tossing a coin is a great way to make a decision. It's that clutch point when you know whether or not you've made the right decision. The ASCAP survey speed, I can give you some of this. So continuum survey speed, typically 350 square degrees an hour at 100 microjanskis RMS. Essentially, you could do the NRAO VLA sky survey in a single day, single 24 hours at the depths of the NVSS. Again, illustrating some of the power of this survey speed. Here is ASCAP on a plot of area in square degrees against continuum depth at 1.4 gigahertz. So the NVSS survey is this probably invisible little green square up here. First survey is here. ASCAP is up here. So it's if you look at the correlation, or at least the relationship, of course, between survey depth and area covered and survey depth, it's the usual survey distribution. ASCAP takes us into a new corner of that particular plot, courtesy of its panoramic capabilities and the ability to image 30 degrees of the sky, 30 square degrees of the sky at once. Oops. So we're up there. So you will have seen the flyer. Well, it's certainly on Ian Smale's door, the flyer for the Australian SKA Pathfinder program. We had a worldwide expressions of interest release a few months ago. We've now proceeded with that to select 8 plus 2 strategic survey programs for development. It's personally very encouraging to me to see the response we've had. 30% of the scientists came from Australia, 30% from Europe, 30% from the US, and 10% from the rest of the world. We had over 360 people are on these 10 survey programs that have been selected from 161 institutions. And of course, we're going to put these 360 astronomers to work. Where are you, Alistair? In order to deliver the data products. It's quite a similar model to the model that was evolved, I think, initially with things like 2DF, where you actually get the survey teams to start defining some of the software. So we've got those teams will be delivering those products, and the data, when they emerge from the surveys, will be released to the worldwide community with no proprietary period. I mean, obviously there'll be a period while the survey teams works on them to deliver the products, but the intention is for these to be made immediately available to the community, worldwide community. So here are the survey science programs that will be done with ASCAP. And I didn't invent these names. And I'm sure Alistair can help me. So we have EMU, which is exploring the something universe. You can so this is the all-sky continuum survey over the 75% of the sky that's visible from the West Australian site down to an RMS limit of 10 microjanskis in the continuum at 1.4 gigahertz. There's Wallaby, which is the wide area L-band survey. Yeah? Something like that, which is an all-sky H1 spectral survey covering the redshift range from, of course, 0 out to redshifts of 0.23.
Sorry, you probably said this and I missed it. What range of depth can you cover?
We can go down to an elevation limit of 12 degrees. So I believe the surveys are going to about, is it plus 10, Alistair?
The idea was that we would try and go to plus 30 if we can.
Yeah. There you go, to plus 30. So as far as we can go. So we have we also have Possum, which so these are the two. We gave them school grades. I think these are the 2 A+ surveys, are they? The two are the 2 A+ surveys. The rest are A or A- surveys. So the 2 highest priority ones will be the EMU and the Wallaby. It will take up the largest part of the time. 75% of the ASCAP time will be reserved for these surveys. 25% will be available for general use. So we have Possum, which is a rotation measurement survey, looking at background sources, determining the rotation measures to get the most detailed map of the galactic magnetic field. There's Dingo, which is a deep H1 survey, going as far as we can go out to redshifts of a half for H1. There's a blind H1 absorption survey called FLASH, looking again at distant radio sources, looking for H1 absorption in front of them, right down to the low frequency limit of the ASCAP, down to out to redshifts of 1. Large-scale galactic survey in H1 and OH, and 2 transient surveys called VAST and CRAFT, which will look at the transient universe. VAST will look at variable objects above 5 seconds, and craft will actually be a commensal transient survey. Simply use the data that's been currently existing to look down at less than 5 second variation. So again, exploring an area of temporal parameter space that's been largely unstudied. Again, simply the large field of view giving the maximum possible opportunity to look for these variable sources. What we'll find there, don't know.
Do we know any sources that vary on less than 5 nanometers?
Very short duration gamma ray bursts.
I mean, I don't know.
Yeah, I mean those are the types of sources that, I mean, the things like the magnetar burps as well. There could be a set of objects. There's also the R rats and things like that in the sort of pulsar area that could easily extend down into that temporal domain that we simply haven't sampled yet. There's two other surveys, as I said, there's two strategic surveys that we don't know whether or not we'll be able to do, and that is pulsar timing. Because the array is spread out, we're not sure whether we've got the central collecting area to be able to do accurate pulsar timing and to do the processing, and also VLBI, that is connecting ASCAP with the other telescopes on the east coast of Australia in order to do very long baseline interferometry. They're important strategically, not least, of course, because they're two key elements of the larger square kilometre array case, but we're not promising anything in these domains because they are well, the whole thing is challenging, but these are extremely challenging. Data transport in particular, and the cost of data transport in VLBI is significant to do wide field VLBI. So for the remainder of the 10 minutes of the talk, we're just going to go through the system diagram. This is how you build a radio telescope. Sorry, it's so you have an antenna. This is actually the testbed antenna that we're using out at Parkes to test some of the equipment. There's no point in trying to test these things way out in the middle of nowhere in Western Australia. Logistics are quite significant, so the logistical problem is quite significant. So we had a small testbed built by Patriot Antenna Systems of the US, which we've had now for a year or so. This is actually, so the antenna then data goes to a feed. This is an image of the prototype checkerboard feed. This is our phased array feed. This is our radio camera. Actually, up there is John O'Sullivan. For those of you who don't know, and you can read it on CSRIO's webpage, of course, John O'Sullivan started life, of course, in radio astronomy, and he's lead author on a patent for wireless technology, 802.11, that CSR recently settled out of court in the US for some that I can't disclose. But if you ever want to make the case that astronomy generates outcomes in innovation, albeit through a long and complicated path, look at the story of 802.11 that we'll be releasing over the next few months, because it's quite an astounding story. And John is a brilliant individual, and in fact, after going through many companies, because they spun out a lot of this from CSRIO, John came back to work for us on ASCAP because he felt that things like this provided him with the greatest opportunity to be innovative in this environment again. So once you go through the feed, of course, the signals are amplified. I'm telling you everything you know. Amplified, and then goes to the processor. We form the beams at the individual telescopes, the beams from each of the elements of the phased array feed. A lot of fiber to the central image generator, the processor, or the correlator, which is, in this case, it's an IBM Blue Gene computer. Don't know whether or not our correlator will be an IBM Blue Gene, but again, an important part of this whole project is our very close working relationship with all these computer companies. We have an industry cluster associated with ASCAP in Australia, over 50 companies. The companies like IBM are very closely involved in all of this in terms of sharing their resources with ours in doing the early research and development for a lot of this sort of stuff. I'll show you later a little diagram we call climbing Mount Exaflop, which shows you why IBM are so interested in this particular issue. And of course, you've got to power the whole thing. And this is, again, strategically quite important. ASCAP will require about 100 megawatts of power. If I was to use diesel, and you'd have to use diesel out in the middle of nowhere, it's off-grid, it costs me about 4 million Australian dollars a year. Even at current diesel prices, and neglecting to cost carbon in all of this, we can't afford to do that. And so renewable energy will be a key component of this. We've got a small renewable energy penetration at the moment in the ASCAP project, but we've got another submission in to do a large-scale zero carbon footprint renewable energy. So not only is it a problem, of course, of generating the stuff, and we're looking currently at solar thermal or even solar photovoltaics, but it's storing the thing, and that's a real challenge for us. So as well as our solar thermal, we're also proposing to have a carbon capture system there too, as well. So that gives you an overall idea. So we'd like, you know, this project to be one of the first large scale. I'm not sure of any other carbon neutral or green telescopes there are around, but it's really very significant. And it's interesting what that does as well is that companies like Boeing are also very interested in this project. Yes, from the point of view of system integration, which is what they do when they build their aircraft, either civil or military, but companies like Boeing are now buying up solar renewable energy companies in the US. Boeing have just bought Spectracon, and Boeing are very interested in partnering with us to deliver these sorts of renewable energy systems as, you know, high-profile systems, leading-edge systems, as part of their business model into the future. So it's a really interesting wrinkle on all of this. Okay, so this is ASCAP antenna number 1. This is it actually moving. This is a picture taken a few days ago at the Chinese factory where it was built. It's a 3-axis antenna, so that means it moves in both altitude and azimuth. And as well, of course, as having an instrument derotator at the front of it. Actually, it's not just the prime focus that rotates; it's the whole telescope that rotates. Why does the whole telescope have to rotate? Because the phased array feed has to maintain the same relationship with the legs of the telescope from the electromagnetic compatibility and the ability to calibrate the phased array feed. So we had to move the whole telescope. Now this was quite a challenging project. There's not many people in the world who make 3-axis antennas in this way, particularly when the third axis is moving all that 12-meter diameter of steel. But this organization called SETSI 54, and yes, there is SETSI 1 right through to 53 and all up the way to 100. It's a former Red Army Chinese company. And so guess why they make 3-axis antennas? Clearly they're experienced in this particular area. I'd have to say over the last year, it's been one of the most challenging things, first of all, to explain to a very, very supportive Australian Minister for Science why the first major contract was going out to a Chinese company and why it was going out to a former Red Army company. And then to explain to the Americans why a Chinese antenna was going virtually next door to their top secret base at Lermont, because it was all going to be filled with spyware and malware to eavesdrop on this next door airbase. Well, next door being 400 kilometers away, of course, but still next door. So a very interesting period, but nevertheless, these guys have delivered this telescope absolutely on time, and this per unit cost of each of these antennas is 300,000 Australian dollars, 150,000 pounds. That's remarkable. I mean, it's very close to the price point required for the SKA that we thought was impossible. And they've delivered a very, very exacting antenna. The actual surface accuracy of this is 0.5 millimeter, which is way more than I mean, I know in optical terms that doesn't sound like a lot, but for a thing that was really only spec'd to run up to 5 gigahertz is really, it's superb. And because, you know, it's like a new parent, of course, you get fed up with the baby photos. Here's another photo that I'm going to show you. So that telescope is actually leaving China today. It's heading off on a boat to Australia today and will arrive at Perth, Geraldton. So I think you can see it turning. I don't know if this one shows you the third axis. Yes, there it goes. You see the whole thing's turning on its central axis. So quite remarkable. Again, an interesting issue of working with the Chinese. When we did the factory acceptance testing, we gave them a huge list of things that were wrong with the telescope, but, you know, essentially in order it was still accepted, but there was little niggles and so on and so forth, particularly around occupational health and safety they hadn't addressed. And you can imagine what the Chinese, they quickly got rid of all their bamboo scaffolding from around the telescope. And it's important for us. So what will happen now is that antenna will be, as I say, shipped. It's being shipped today, and will arrive at Geraldton in the middle of November. There's going to be a little civic celebration. Local priest is going to bless it. I don't know what's going to happen. They're going to bless it or something like that, and goes out to the site for mid-November. So it's there. And to be honest, after all the hassles we've had, particularly with our Australian industry cluster, being quite vocal about saying, you made a mistake and we're just waiting for the Chinese to fail, it's really good to see the Chinese making it in an amazing way. Of course, another key aspect is the supercomputer. This is what we call climbing Mount Exaflop. This is a little graph showing you the performance in gigaflops, teraflops, and petaflops of the red line here is the fastest computer in the world. That's the sum of all computers in the world, and that's the 500th fastest computer in the world. And this is, of course, just simply Moore's law. As everyone's aware, that is a doubling of processing power every 18 months. This is where we need to be for ASCAP. ASCAP, approximately a 100 teraflop machine, which is quite puny by world standards currently. The fastest computers are about 1.5 petaflops. But still, nevertheless, very much an increase on what we've done before in radio astronomy. And it's part of that growth curve that we have to track if we're actually to deliver the processing power required for something like the square kilometre array on the 2020 timescale. Full SKA would require of the order of 1 exaflop, which would be the fastest supercomputer world at that stage. And again, it's another reason why companies like IBM, Cisco Systems, Dell, well not Dell, but SGI, actually are very interested in the sort of technologies. We've just actually awarded work on the research and development on our single digital backend to IBM as part of a collaborative R&D program. And that, of course, adds value to the overall project. This is the green power problem. So ASCAP will use a megawatt. Ultimately, with the SKA, we're talking about 100 megawatts or greater of power. This has to be managed. You simply can't do it with fossil fuels. At least I certainly wouldn't want to do it with fossil fuels. The cost, particularly if you price in carbon into it, will be significant. So at the moment, we've got a proposal into the Australian Education Infrastructure Fund, a sustainability round for a significant amount of money in order to pay for not only the costs of putting the solar thermal power station out at the radio telescope site, but also to power the supercomputer, which will be based back at Perth using geothermal power. So we're looking at the system as a whole to be carbon neutral. So this is just to give you an idea of where ASCAP is. This is just almost a little cartoon of where a potential SKA antenna configuration across Australia would look like. SKA will comprise about 3,000 10 to 12 metre dishes splayed out in about 150 array stations across the continent. Most of those will be in the central region. Half the antennas will be within a 5 kilometre by 5 kilometre region. But there'll be a number of stations, up to 20, scattered more broadly across the continent. And New Zealand actually has just formally joined Australia in proposing to the SKA and adds 2 array stations, one down in Invercargill and one up just north of Auckland, potentially increasing the baseline from 3,000 to 5,000. Although this doesn't look like a perfect spiral, if you actually look at the logarithmic spiral, New Zealand falls on the next logarithmic spiral arm away from Australia. So really very conveniently located. Yeah, the thinness and the orientation of New Zealand fits the SKA perfectly. Let's just blow up this particular region so that you get some idea of where the telescope is being placed. This down here, this is the west coast of Western Australia. This is the delightful town of Geraldton, the site of the Murchison Radio Astronomical Observatory, where ASCAP will be based, and the Australia's core site, candidate core site for the SKA is here. As I say, it's in the Shire of Murchison, which has no towns. It's actually quite pleased with itself in having no towns. It has a total population of 110 people. It has a size, just so to give it some sort of size, it has a population just slightly larger than the Netherlands. Sorry? Sorry, it has a population. I beg your pardon. An area just slightly larger than the Netherlands. So a population density of about 3 nanopeople per square meter. So it's one of the most isolated spots in the world. Why do we go there? Of course, whole issue is freedom from radio frequency interference. In the same way that optical astronomy, of course, increasingly is dominated by light pollution, radio astronomy is no different. In fact, it's even worse. While there have been bands in the past protected, for example, the 1.4 gigahertz H1 line, of course, is protected. With going deeper and deeper into the universe, of course, things are redshifted, galaxies are redshifted into the aircraft band, mobile phone band, and of course, ultimately, epoch of ionization is probably pretty close to the FM band. So you've got to go somewhere pretty special in the world in order to avoid all those things. This is the Murchison Radio Astronomy Observatory. For scale, that's a caravan just up there. It's a wonderful place, actually. It's the SKA site, or the ASCAP site, I should say, is roughly in this upper region. Will be in this upper region here. We're getting onto site on November the 15th. Why can I say that date so precisely? Because that's the date at which the registration period for native title ends. One of the very important aspects of this is to have a negotiated relationship with the native title claimants of the land, the Wajidi-Yamaji people. And in order to put radio astronomy telescopes on there, one has to change the use of the land, which from pastoral use to pastoral plus radio astronomy use. And in so doing, you negotiate that with native title claimants. That's all been done so that we do have a very good relationship with our indigenous population at the site. You can get people there. This is two quite important people. That's on the left is the Minister for Science, who was out there a couple of weeks ago, the Australian Minister for Science, who was out there a couple of weeks ago. On the right is Mark Helene, who runs the station. He's the station manager. One of the ways to protect against RFI is actually to own the station. So CSRIO now owns the entire station on which the Murchison Radio Observatory is based. The station is 3,400 square kilometres, which is about 50% larger than County Durham. So CSIRO increased its land holding by a factor of 100 in one fell swoop, and we got the West Australian government to pay for it. So that's again very nice. This shows you also the other thing that you have to do beyond just simply buying the station. You have to protect more broadly for radio frequency interference. So we've got the central Murchison Radio Astronomy Observatory, which the very central location, which would be the centre of an SK, the 5 kilometre by 5 kilometre central region. We've actually excised under the native title negotiations a significantly larger area of 127 square kilometres, sitting within the 3,000 kilometres that we own. And then more broadly, working with the Australian Communications and Media Authority, we've actually put down what we call a radio astronomy licensing instruction, so that actually prevents fixed broadcast transmissions from this region. So we've now got about 2% of Australia that is under this management, and it's essential. If we're to protect this site, if this site is to be the site for next generation radio astronomy, we've got to protect it for the next few generations. So that's really important.
So where is the big right
Up here, yeah, Lambeth. So we're a long way away from it. This final radius is 260 kilometres. We're also rolling out fibre optic in the next month, and it's going from here into Geraldton. Initially, we were going to have our supercomputer processor in Geraldton, where the operation space would be run from. About 12 people would run out of Geraldton. However, the government then subsequently announced a high-performance computer in Perth, a petaflop machine in Perth, and so we decided that we would use that instead, because the government also announced as the first rollout in Australia's government has invested $43 billion in what they call the National Broadband Network. That's rolling out a new network. The first tender for that network, first cab off the rank, was the Perth to Geraldton fibre optic link, precisely because of the SKA. And they've provided us with 10 additional fiber pairs on that link in order to run the data down from SKA. So it's it has a significant profile in terms of not only a radio astronomy project, but underpinning some of the infrastructure development in Australia. Oh, it's the radio coordination zone. And what else have I got for you? Oh, I've tried to avoid showing you animations and stuff that we've actually done, but I couldn't resist showing this beautiful animation from Swinburne University, which has stopped. Well, you don't get to see any more. Well, you got to see a bit of it. So anyway, that's what I have to say. So that gives you, I think, a flavour overall of where we are in the project, what the science has been done with the project, and the relationship that we're building up with industry and the case in future for the SKA, and a little bit about the telescope site too. So thanks very much for your time.
Presumably you've got another page waiting for this question, which is what is the punchline, bottom line science that MU and Wallaby or A-grade proposals are going to do? It would encourage you to spend this huge amount of money, which you magnificently got out of the Australian government.
I can never remember which is which, to be honest. I mean, essentially, the H1 survey provides us with almost a comprehensive picture of H1 in the local universe, albeit out to redshift of 0.2. But it does give us an ability to compare the H1 with the stellar distribution that we're seeing from the optical to put together a rather more complete picture of Galaxy University. Oh, out to redshift of 0.06 with high pass. So we're extending it a factor of 5 further in terms. So.
What's the science gain? What's the science gain in that factor? So you're doing redshift surveys from the 21 centimeters?
Yep, from the 21 centimeter line. So first of all, the increase in volume, of course, you're going at a factor of 5, so you're going at a factor of 100 in volume. You're increasing the number of galaxies by 100. Now, I could ask the same question, why do you do any optical survey a factor of 100 more? And there's very good reasons across, evolution, across the clustering, looking at clustering of galaxies and the environment of galaxies. So it's all those same arguments apply to the way of increasing an optical survey by a factor of 100.
Sometimes BAO, this area of volume is going to essentially it's been done already by, well,
Not in H1.
no.
Not in gas.
No. But the BAO is,
But we're not doing. I don't think I said BEO, did I?
no. That's one of the reasons
So I'm sorry, Tom, but I can't defend something I'm not doing.
it's what the anyway, so it's basically a survey, 15 arc second, did you say?
Yeah, resolution. Yep.
Basically, it's evolution out to 0.26.
Evolution out to 0.26 in H1, and all the cluster, the cluster and environmental properties, H1 relationship out to there, and it's also increasing. Alistair, I mean, what's the total number of galaxies? Yeah.
That's not an end in itself.
No, but I'm trying to indicate what the difference between that and the Parkes high pass survey. High pass surveys are there 1,200. So again, it comes down to other people who use surveys who will say then you can then split things into different bins, and so it's the argument of how much statistics you have in each of the bins. So you're splitting things to 10 bins of H1 mass and 10 bins of redshift. You go from 1 object per bin to 100 objects per bin.
And the continuum surveys.
Yeah, the continuum survey goes a factor of 100 deeper than NVSS, and a factor of about 6 or 7 in terms of resolution. So what have we done with NVSS that's been helpful? I think it's been a very significant survey, but it doesn't match currently the depths that we're looking at in terms of the deepest imaging we're now doing with 8-meter class telescopes. I'm not saying that ASCAP will match the depths. It's only going to go out for continual objects out to a radius of 1 or so. Will provide a much more matched set of data to look at issues of star formation over that period in terms of the radio emission, star formation versus AGN properties over those sorts of redshifts. So everything we got out of the NVSS, we would hope we would get out and more from the. We had to get a factor, an order of magnitude, or 2 of magnitudes more from surveys like this. From things like you asked me, you said, what's the elevator pitch? Well, I can't give you an elevator pitch from this one because essentially it's going 2 orders of magnitude faster in survey speed than any other radio telescope's ever done. So is there what's going to be the killer science result out of this? I can't tell you, Tom. It's probably something I haven't even thought. We haven't even thought about yet. But things like the magnetic field, it'll be the first time we've ever looked at the magnetic field across the galaxy at sub-arc minute resolutions. So actually looking at the detail of magnetic field and how it relates to the stellar and the gas distribution in the galaxy. And for those people that do the galactic archaeology in the Milky Way, that's a godsend. I mean, I remember getting told, I think you probably told me as a PhD student, if you run seminars, the one question you can always ask after incomprehensible seminar is, have you considered magnetic fields? And because we simply don't know about it. It sounds like you, doesn't it, Tom? So, I mean, this will be the first detailed magnetic field, first detailed map of the magnetic field of our own galaxy. Those sorts of resolutions. So those are some of the things that I think it'll do.
To justify using renewables, you really have to have a long time run the system.
The current survey program would last for 5 years. Now, of course, obviously, we want ASCAP to last beyond its initial surveys. Indeed, we'd want ASCAP to grow ultimately into the SKA. So you would hope that the lifetime of any facility like that is measured in decades. And if you look at any telescope, and we kind of in Australia we've used the example of Parkes. Parkes was built in 1961, and it's still doing good science today, 50 years later. So we work on a sort of 50-year baseline for that, John. You're right. Although having said that, it's almost not an economic argument at the moment in terms of the power, in terms of paying it back. It's actually a developmental argument as well, because we want to work with companies in Australia that will help do the R&D. Yes, absolutely. It is a subsidy, and Australia's in an interesting position. Australia's actually a little bit behind everybody else in solar because it has a lot of coal, and so you can't. Yeah, exactly. Yes, absolutely. So countries like Australia and South Africa share the same problem: plenty of sun and coal, and it gives rise to a horrible policy issue. We're not clear yet. We're talking about 6 terabytes a night of processed data. At the moment, we're planning to try to keep all of that in terms of generating petabyte data sets, and it's one of the areas that we're working with our industry collaborators in order to deliver that sort of storage materials on the 2012 timescale. Whether we get there or not, I can't tell you at the moment. If you project the growth of data storage, which doesn't go quite as fast as Moore's law, we still think we'll get there.
I mean, do you think it's going to work? Collaborating industry, because certainly the information that we've got from what happened with Castor, with Boyle developing the software to take off the satellite,
The stuff that we've done today with industry has been successful. I can't say whether or not it's going to be successful. What we're not going to do is simply give them a contract to do something. So, build us this. It's going to be something that the industry come in and work with us right from the very early stages. So if things are going off the rails, for example, if they're diverging away from us, we'll simply say, well, this is not going to work. The last thing we want to do is to essentially give them a contract and say, just go away and give us it when you're finished. So it's one of those things. It is a much more collaborative mechanism rather than a purchaser-provider relationship. That in itself gives huge problems because an organization that I work for, like CSRIO, is very, very careful about its own intellectual property, particularly after being successful, well, settling out of court around contending with a patent about wireless LAN. So that's a real issue, John. It's something I don't know whether or not we're going to resolve. And frankly, it is an area where I think we've been least successful here, is making sure that the intellectual property aspects are clearly defined between what we are doing in these collaborative ventures and industry. Yeah. Oh, well. Yeah. Well, lawyers are a fact of life. I'm married to one, so. And believe you me. Believe you me, if you've ever been involved in native title negotiations, you've seen lawyers.